So hello everyone, my name is Labani and currently I am at IIA Bangalore working on supermassive black holes, and today I'll be presenting our recent work on the detection of soft and hard X-ray time lags in a sample of very low mass AGN, and this work was done in collaboration with many scientists all over the world. But before I begin to talk, I would like to thank the organizers for this opportunity to present my work, and also the Department of Science and Technology for the support. So this would be the outline of my talk. First, I'll start with a brief introduction of AGN energy and time lag spectra. We'll talk about various types of time lag that we generally observe in higher mass AGN as well as in stellar mass black hole binaries. And then we'll talk about the motivation behind this particular work and our science goals. After that, I'll describe the source sample that we have employed for this work, and then we'll explain the results. Basically, I'll show you the lag frequency spectra for this low mass AGN and how this AGN helped to update the existing scaling relations between the black hole mass and the soft lag. We'll also explain the origin of soft and hard lags through physical modeling and how these lags can be used to constrain the size of the corona after considering various effects that are present close to the black hole. And at the end, I'll summarize the results. So in this slide, I'll introduce you to the X-ray emitting region or the corona, which is basically the plasma of very hot electrons surrounding the supermassive black holes, and most likely it is located above the surface of the accretion disk or on the plane of the accretion disk. We think that it is the corona which is accounting for the primary X-ray emission from the AGN that I have shown here by this red dash dotted line. And this primary X-ray emission mainly dominates the 1 to 4 kb band in this range. But due to strong gravity close to the black hole, due to strong gravitational effect, a fraction of X-ray emission from the corona gets bent down onto the accretion disk and produces reflection features. These reflection features then get blurred, broadened, and shifted because of various spatial and general relativistic effects. And therefore, what we actually observe is the blur reflection spectrum, and which is shown by this blue dashed line, and this blur reflection dominates 0.3 to 1 kb band as well as the 4 to 7 kb band. But for this particular work, I'll be only focusing on the soft X-ray band, which is the 0.3 to 1 kb band. So as you can see from this right hand side, this figure, that we expect to see some delay between the direct emission from the corona and the secondary reflected emission from the accretion disk. And this delay can be either positive or negative, depending on the emission mechanism and the time scales that we are probing. So when this hard band dominated by the coronal emission lags behind the soft band, we observe a positive or hard lag. And this lag is detected usually at lower frequencies. On the other hand, when the soft band dominated by reflection lags behind the hard band, we observe a soft or negative lag, and this lag is generally detected towards higher frequencies. And this kind of time lags profile has now been observed in many higher mass AGN as well as in stellar mass black hole binaries. And this spectra contain a lot of information about the black hole environment, and they can be used to map the geometry of the extreme environment just outside the event horizon of the black hole. And above all this, we see a very strong correlation between the soft lag frequency, amplitude, and the black hole mass for a large number of high mass AGN. So this tells us that there is a good chance that we might detect similar kind of time lags for the low mass AGN. And with that purpose, we explored the low mass end of AGN and searched for both soft and hard lags in this class of AGN. Then the second goal was to extend this existing black hole mass versus lag scaling relations and provide a complete assessment of the lag mass correlations for a broad mass range. And then this will actually help to test the unification theory of black hole accretion. This will help to test the unification theory of black hole accretion, and we'll be able to confirm the existence of black hole mass independent accretion properties. We also aim to understand the origin of both soft and hard lags through physical modeling. And for this purpose, I surveyed the entire XMM-Newton archive and found a sample of 26 low mass AGN. But the application of various filters, for example, the background noise, exposure time, the source type, led to a final sample of only 8 CFAT1 low mass AGN. And here you see the lag frequency spectra for these 8 low mass AGN. The time lag we estimated between the soft 0.3 to 1 and hard 1 to 4 kV bands. And the negative lag means soft band variations are delayed relative to the hard band. The hard lag amplitude corresponds to the maximum positive point in the lag profile, whereas the soft lag amplitude refers to the maximum negative point in the profile. And this soft lag I have shown by this black arrow here. So as you can see that these soft lags are observed at higher frequencies, so the corresponding variability time scales are shorter. So the number of photons collected per soft lag beam is lower. Therefore, it is always the soft lag which is more challenging to detect. And for that, we had to make sure that what we are getting is the real lag and it's not something due to Poisson noise. For that, we did simulations. The CI here represents confidence interval for the detection of soft lag. And we find that 6 out of 8 AGN are showing robust detection with 90% confidence. Then we examine the correlations between the soft lag amplitude frequency and the black hole mass for the combined sample, which consists of 6 significant detection from our sample and 15 AGN from the literature. The fitting of these datasets with the linear regression model provides the best fit scaling relations, which I have listed here. The solid black line here, it is the best fit linear model, and the red area represents 1 sigma confidence interval. These scaling relations are pretty much consistent with the existing scaling relations though. Now the question is, what could be the origin of these lags and how we can use these time lags to constrain the geometry of the corona at the size of the corona. For example, if we consider that the corona has a lamppost geometry and it is isotropic, stationary, and is located above the rotation axis of the black hole, then on shorter time scales, the variability in the disk reflected emission should lag behind that in the direct coronal emission. So the soft lag here is explained in the context of disk reverberation, where disk reverberates in response to the primary coronal emission. And the soft lag amplitude can then correspond to the light crossing time delay between the corona and the accretion disk in flat spacetime. So in flat spacetime, we can estimate the time lag, reverberation time lag, using this simple equation. But in reality, close to the black hole, when light propagates, it gets delayed because of GR delay or the Shapiro delay. So the photon takes longer time than what is estimated from this simple equation. The right-hand side plot here showing reverberation lag times as a function of coronal height for both flat and curved space-time. For the flat space-time, the lag was estimated using this simple equation. But for the curved space-time, we estimated time lag using the reverberation model of Wilkins et al. 2016, where we have considered all of the light paths from the corona to the disk to the observer, as well as the Shapiro delays. So after correcting for these effects, we find that the corona of the sample extends at an average height of around 10 RG. And this value is consistent with other measurements, for example, microlensing measurements, and this is also consistent with the reverberation with the coronal height of higher mass AGN. The hard lag, if you remember, it was observed at the lowest detected frequencies, and the corresponding time scale was around 30 minutes. So the origin of this lag can be explained with the propagation of luminosity fluctuations through the corona, although the origin of the fluctuation was the outer disk, but the fluctuations propagates through the inner accretion disk and then it hits the edge of the corona, and from there it again propagates through the corona. So it is basically the time lag between the edge and core of the coronal emission, where the soft X-ray photons are coming from the edge and hard X-ray photons are coming from the core of the corona. Therefore, the hard lag can actually correspond to the viscous time delay between the core and edge of the coronal emission. So, from this hard lag amplitude, one can estimate the coronal radius using this equation, where this HC is the coronal height that we have already obtained from the soft lag. So after considering various effects, we then find that the corona of the sample extends at an average radius of around 6 Rg, and this is consistent with the disk break radius obtained for higher mass AGN. So in conclusion, I can say that the nature of the lag frequency spectra is very similar to what we observe in higher mass AGN as well as in stellar mass black hole binaries. The origin of soft lag can be explained in the context of disk reverberation, where disk reverberates in response to the coronal emission, where the corona has a lamppost geometry of height around 10 Rg. The hard lag we can explain with the inward propagation of luminosity fluctuations through the corona of average radius around 6 Rg. The correlations between the black hole mass and the soft lag frequency as well as amplitude for a very broad mass range suggest the presence of a mass-independent accretion process in accreting black hole systems. And this work is just the beginning of more comprehensive investigations into the low mass end of AGN, which are crucial because they can provide significant constraints on the nature of primordial supermassive black holes, and therefore it can provide important understanding of cosmological black hole growth models. And with that, I'll stop here, and thank you so much for the attention.